Hello everyone. In class on Friday we had what was supposed to be the most amazing day of your life, which was a proof that there are only 5 Platonic solids. And okay, just really quickly, this is our Jamboard from class. What did we do in class? We looked again at the 5 Platonic solids, counted their number of faces, vertices, and edges, noticed that there's some kind of pattern, and then we gave a kind of informal geometric proof that there are only 5 Platonic solids. And okay, I had some terrible pictures, so I thought I'd just bring to your attention a nice picture that I found on Wikipedia where there are a lot of pictures. And here they introduced this term that I may have mentioned this in class or I may not have, but anyway, I'm going to mention it later, this term called defect. What is defect? It's the failure of the polygons meeting at the vertex of a polyhedron to add up to 360. Maybe we shouldn't call them failure. It's the amount by which the sum of the angles of the polygons meeting at a vertex of a polyhedron. I forgot the beginning of my sentence, but it's the sum of all of them less than 360. 360 minus the sums of the angles of all the polygons meeting at the vertex of a polyhedron. Okay, picture's worth 1,000 words. Here you see, as we discussed in class, that if you try, this is just a complete repeat of what we already did. Maybe I should do this like really fast or not at all. But remember we said, hey, suppose you're trying to make a triangle with 3 meeting at a vertex. Well, here is just a more beautiful picture of what I was trying to draw, which is that if you try to do so, there's room. In fact, there's a defect of 180 degrees, is what it says right here. And that defect of 180 degrees means you have 180 degrees of freedom to fold those 3 up. And then we said, well, what if you're trying to make a shape with triangles and you have 4 triangles meeting at a vertex? Perhaps this was totally clear in class, but perhaps it wasn't. So if you put these 4 triangles all in a row like this, then you have a defect of 120 degrees. In other words, you have 120 degrees left of room to fold them up. And if you try to put 5 triangles together at a vertex, then this is what it looks like. This is exactly what I drew, but just prettier. And therefore maybe easier to understand. You have a defect of 60 degrees, so there's still space for you to fold those triangles up and you get the nice hat. But what we said is if you have 6 triangles and you try to put them together, well, you can, just barely, and then you have a defect of 0, and so it's completely flat and you can't fold them up, so you just don't get a polyhedron there. And here's just some more, here's just the rest of the argument, right? If you give me squares, you can put 3 of them together and you have a defect of 90. But if you try to put 4 of them together, then you have, once again, a defect of 0, so you can just barely do it, but you can't fold. Finally, here I didn't even try to draw it because I thought my picture was going to be so bad, but this picture is beautiful. If you are going to use pentagons, you can put 3 of them together, and because they're 108 degrees in every angle of a regular pentagon, then that's 324, so you have 36 degrees left over here to fold those pentagons up. And, okay, so good job. But if you try to put any more than 3 pentagons together, it's just like not going to work. And finally, with hexagons, if you try to put 3 of them together, then you're going to have, again, a defect of 0. And so actually, these 3 cases, this one, and this one, are sort of interesting because they lead to what are called tilings, regular tilings, but we might as well call them Platonic tilings. They're a way of tiling the plane, and so they kind of fit in this chart. So maybe it should be somehow like a different color for the ones that you can't even do that with. So maybe I should turn this frown into a happy. This is happy. This is happy. And this is happy because these 3 produce tilings, and the other ones are just like even worse because in Euclidean geometry you just can't even fit that many together, let alone having positive defect left over to fold up. All right, this was already like 8 minutes that I kind of wasted because I didn't really even want to talk about this. What else did we do? We did this proof that maybe you understood and maybe you didn't of the one of the old proofs of Euler's polyhedron formula. And then we proved, I thought decently, but maybe not perfectly, this theorem, Euler's formula, but as applied to simple planar connected graphs. Okay, and then there was this, and I just think this is just too wonderful to have done sort of badly. So I'm going to just redo this proof. You can watch this at 2 times speed or not at all. And okay, here we go. Perhaps this is where the video should have started. There are only 5 regular polyhedra. Why? Well, what does it mean to be a regular polyhedron? We have, is this working? Yeah. Ooh, look at this. This is what I should have done in class. Here we have a cube, of course, and we can just rotate it around, and it's amazing. And we have here a dodecahedron and, you know, an octahedron. Octahedron. Whoa. Okay, so these are, of course, the geometrically regular versions in which the faces are all regular polygons. But I want my theorem to apply more generally than that. And so here I have, just as I did in class, I put regular in quotes because now I no longer want them to be regular in the geometric sense, merely regular in the topological sense. And I'm assuming you all know what that means. So I'll just keep repeating myself. What does it mean? It means that what does it take for the polyhedron to be regular according to this more relaxed definition? Simply that all of the faces of the polyhedron are the same kind of shape. In other words, have the same number of sides. So, for example, you are going to build your polyhedron entirely of triangles, or entirely of squares, or entirely of pentagons. That's one property that I demand. The other property that I demand is that every vertex is the same with respect to the number of polygons meeting at that vertex. And so, in other words, if you are going to make your polyhedron out of triangles, then there should be 3 triangles meeting at every vertex, or 4 triangles meeting at every vertex, or 5, or 6, or 7, or 8. I'm going to prove to you that, in fact, 6, 7, and 8 are not possible. But I'm going to prove it using only that feature. Okay, and so here we go. Let's just introduce this is a complete repeat of what we did in class, but maybe just better. So so take a particular polyhedron. And first, let's count the number of edges. Let's let the number of edges be epsilon. I just got this notation from our textbook. Let the number of vertices be V. And let's let the number of regions or faces be R. Okay. And okay, the reason why I'm just redoing this proof is because this is just like one of the proofs of your life, and so it really needs to be like in your brain on a deep level. So it's worth doing again, maybe slower. Okay, so this is just an arbitrary polyhedron at this point. It has a certain number of edges, a certain number of vertices, and a certain number of faces. And sort of towering over this entire discussion is that any polyhedron, in quotes, not really any spherical polyhedron, any polyhedron with this certain kind of topological property that it is kind of spherical, can be stereographically projected down into the plane, and it becomes a simple planar connected graph. So you can either apply that fact and cite Euler's polyhedron, Euler's formula of graph theory, or you can just do a direct proof about polyhedra. But one way or another, we have already proven, I'm taking it as a central background, previously proven fact, that we have Euler's formula. So that the number of vertices plus the number of faces minus the number of edges is 2. Okay, well, now I am going to use the fact that it is regular. And in the specific way I've defined regular, that that every, that we're using the same kind of shape, and also that there's the same number of them meeting at every vertex. And so let's let the degree of each vertex, let that be n. And what does that mean? Let's just and then the number of edges bounding each face, let that be b. Okay, so I have these kind of like 5 numbers, and number of edges, number of vertices, number of faces. The b represents just the kind of polygon it is. If you're going to do it with triangles, b is 3. If you're going to do it with squares, b is 4. And n is just the number of them meeting at each vertex. And then the other thing we discussed in class is, but I just said it, very, very fast, but I think this is pretty reasonable, that like, first of all, well, 2 things. One, maybe this one's even more kind of obvious to start with, that what kinds of polygons are there that we can use to make polyhedra? Well, triangles, squares, pentagons, hexagons, etc. But like, any polygon has to have at least 3 sides. So b has to be greater than or equal to 3. There is just no such thing as a polygon with 2 sides. I mean, really, there are always ways mathematicians can push things in strange cases, but basically that's key. And the other key here is that just in order to be a polyhedron, there have to be at least 3 polygons meeting at a vertex. You can't have a polyhedron if at a vertex only 2 polygons are meeting there. It sort of can't kind of close around itself. And again, this is going to be some sort of boring and maybe low-level sort of geometric fact capturing some kind of fundamental assumption about polyhedra that could be used to justify that if someone pushes back. But let's just take that as a pretty minimal demand. Okay, so with this only, now we just do the proof. Exactly, this is exactly what we did in class. And what we did in class was to make 2 arguments. And okay, they're very simple in retrospect, but I did them just too fast, I think, for some people. And the argument is a counting argument. It's a way of so let's go. What are the 2 counting arguments? We'll just take any polyhedron. Go to every single vertex. Look at every single vertex at how many edges are incident with that vertex, otherwise known as the degree of that vertex. Well, if you go to every single vertex and you count, go to this vertex, 1, 2, 3, 4. Go to this vertex, 1, 2, 3, 4. And you count them all up. Well, what have you done? You've counted every edge twice. Every edge on this polyhedron is incident with precisely 2 vertices. And by going through every single vertex and counting all the edges that are incident with that vertex, you've double counted every single edge. This is just handshake. Okay, and therefore, I take the number of vertices v times the degree at each vertex, the number of edges incident with that vertex, and that is twice the number of edges. Exactly what we did in class, just a little bit more slowly and with this beautiful animation. Similarly, we may go and take the faces one at a time. So take every single face and just go to that face and say, hey face, how many edges bound you? So for example, here's a triangle. There are 3 edges here, so count them. Go to the next face, count 3 more. Go to the next face, count 3 more. Well, in fact, what have we done? We've counted every edge twice. That's because every edge is on 2 faces. And so by going through every polygon and counting the number of edges that constitute that polygon, then we've double counted every edge. I think that's pretty clear, right? Count 5, go to the next face. Count 5, go to the next face. Count 5, we've double counted every edge. All right, so that's extremely convincing, and maybe this will help some of you. So what does that mean? Take the number of faces, R, multiply by the number of edges on each face, B. Remember, B just captures whether it's B is 3 for triangles, B is 4 for squares, etc. And what I've now done is double count all the edges. Okay, well, if this is true, now I may sort of rewrite this. What this does is provide a connection between Vn and epsilon and Rb and epsilon, such that I may now rewrite the number of vertices as twice the number of edges over the degree of each vertex, and I may rewrite the number of no, that's not what I want to do. I want to rewrite the number of regions, or just the number of faces. That's what R is, right? Yeah. So the number of regions is therefore just twice the number of edges over what you might call the degree of each region. The degree of each region is just the number of edges bounding that region. In other words, B is just the number telling you, what kind of shape you have. Okay, and then, just as we did in class, I'll take this, stick it in here, and I'll take this and stick it in here. Don't like that arrow. Stick it in here. Okay, and so what do we get? We get that twice epsilon over n plus twice epsilon over b minus epsilon is 2. And now I'm going to divide all three sides of this by 2 epsilon. That gives me 1 over n plus 1 over b. And if I divide this by 2 epsilon, I get minus a half. And if I divide this by 2 epsilon, I get 1 over epsilon. Okay, and so the sort of like amazing and incredible formula that I get is that 1 over n plus 1 over b equals 1/2 plus 1 over epsilon. I'm going to put a big box around this, exactly what I did in class, and I'm just going to note, what do we have here? We have here sort of a sort of definitive relationship between these three quantities. The degree of each vertex, the number of edges bounding each face, and the number of edges. And okay, these all those sort of terms in this box are all positive, and all of these numbers are positive. And so I now just note some kind of arithmetic facts, and these all have to be integers. So we have this equation in which n's a positive integer, b is a positive integer, epsilon is a positive integer. In fact, n has to be greater than or equal to 3, and b has to be greater than or equal to 3. And so sort of using like only these facts, right? This fact, this fact, this fact, and the fact that they're all integers, I'm going to now prove to you that there are only 5 possible combinations of n and b which satisfy the condition that they be integers, that n be greater than or equal to 3, that b be greater than or equal to 3, and that this formula holds. Okay, and the key insight here is that only relatively small numbers are going to work. Because if n and b are kind of big, like, I don't know, just imagine like n is like 8 or something and b is like 7, well, that's just not going to work. Because 1/8 plus 1/7 is just much less than a half. And so somehow the left-hand side of this equation has to add to at least a half. And in fact, has to be more than a half. And so just like sort of note that one way of interpreting this equation is that 1 over n plus 1 over b has to in fact be greater than a half, because we do need to have some edges. Okay, and so there's only just a certain number of positive integers, n and b, such that the sum of their reciprocals is bigger than a half. And we just count them all, and that's the whole thing. Okay, so now what I tried to cram into a very, very small window of time, like actually it was no time, is this argument, which we're going to sort of do right now. So here we go. 1 over, what did I say? 1 over n plus 1 over b plus 1 equals 1/2 plus 1 over epsilon. So now a slow and careful explanation of what we did in class, but this time sort of with care and joy or something. Could you have, this is that chart, right, with various values of b along the top and various values of n along the for each row. So could you have a case where b equals 3 and n equals 3? In other words, could you have a case where you had put triangles together, 3 meeting at a vertex? Answer, yes. Triangles, 3 meeting at a vertex is in fact the tetrahedron. And so, just to sort of make this chart kind of beautiful. I shall now, what am I doing? Boom. Tetrahedron. And hey, by the way, notice that, okay, so if b equals 3 and n equals 3, then in fact what we get is like 1/3 plus 1/3 equals 1/2 plus 1 over epsilon. And in fact we can just solve this, right? And we get 2/3 equals 1/2 plus epsilon. What's 2/3 minus 1/2? 2/3 minus 1/2 is 1/6. And so in fact, I've just proven to you that epsilon is 6. In other words, I've just proven to you, in fact, that it's not just your kind of imagination or intuition or whatever, that the tetrahedron must have 6 edges. Okay, so let's just do the rest of these, but like faster now or something. Could you have triangles 4 meeting at a vertex? Yes, you could. If you have triangles 4 meeting at a vertex, then that is the octahedron. And with this octahedron now, what do we see? We see that n is 4, so that's 1/4 plus 1/3 equals 1/2 plus 1 over epsilon. Now we just do a little bit of arithmetic. What's 1/4 and 1/3? It's like 7/12. So minus 6/12 is 1/12. So in fact, I've just now proven to you that an octahedron has 12 edges. It's pretty exciting. Oh, okay, what now? Could you have triangles 5 meeting at a vertex? You really can. And what do you get? You get, look at how professional this is. Miss Rose, why hadn't you prepared this beautiful stuff prior to class on Friday? Don't know. Okay, if n is 5, so now this is 1/5 plus 1/3 equals 1/2 plus 1 over epsilon. And so, okay, well, what is that? That's 3/15 and 5/15, so that's 8/15 on the left-hand side, minus 1/2, so 8/15 is really like 16/30 minus 15/30, so that's 1/30. And so just by doing a little bit of arithmetic in my head here, I've now proven to you that an icosahedron has 30 edges. And now you might ask, hey, all right, where does this argument go wrong? Aren't we supposed to be somehow proving that there are only 5? It seems like everything just works. No, not everything works. Because if b is 3 and n is 3, what do we get? Well, what we in fact get is this. One of these tilings that I mentioned earlier. And now, if you kind of do this, right, if n is 3, because this is supposed to be purely a numeric kind of discrete argument, you get like 1/3 plus 1/3 equals 1/2 plus 1 over epsilon. And now, no, not 1/3 plus 1/3, 1/3 plus 1/6, because n is 6, so that should be a 6. I actually haven't been, have I been consistent? Yes, I have been. 1/6 plus 1, so now you sort of see the problem, right? 1/6 plus 1/3 just is 1/2. And so the left side is 1/2, the right side is 1/2 plus 1 over epsilon. And so one answer to this is that it's just impossible for this equation to be true, because epsilon must be some positive number, and therefore there just is no polyhedron whatsoever. That is completely true. Another way of looking at it is that if n is 6 and b is 3, then 1/6 plus 1/3 is 1/2, and so you get like an infinite number of edges, and you can actually sort of think of this tiling as infinite, because there are an infinite number of edges. In some ways, this is the plane is kind of like a sphere of infinite radius, and so you sort of can make a polyhedron, so to speak, with 6 triangles meeting at a vertex, but it's a polyhedron which is of infinite size because it has 0 curvature. It has to curl around. I'll leave that there. Okay, I gotta go in like 2 minutes, so I should probably finish this off. What if we're gonna do it with squares? Well, if you have squares, 3 meeting at a vertex, is there such a thing? Yes, that is the cube. And so, boom, cube. And let's look at what's going on. What is it? N is, so I get 1/3 plus 1/4 equals 1/2 plus 1 over epsilon. And okay, it's going to turn out that I've already sort of done this math over here, right? And therefore, it must be that epsilon is 12. And that's not a coincidence, because the cube and the octahedron are duals of each other, and they're going to have opposite n and b values. Okay, what if I want to use squares for meeting at a vertex? Well, that cannot be done. Or rather, it can be done, but you will get, once again, not a polyhedron, but a tiling. So now if you write this as 1/4 plus 1/4 equals 1/2 plus 1 over epsilon, then the left-hand side is already a half. And so again, you get epsilon equals infinity. And if you try, here I didn't include another row, but if you try to keep going beyond this, you'll get that 1/5 plus 1/4 equals 1/2 plus 1 over epsilon, and that just doesn't work, right? You just can't have epsilon being, the left-hand side is just less than a half, and so this just doesn't work. And so for all of these, you just get kind of nothing. Okay, last one, what if you're having pentagons with 3 meeting at a vertex? Well, that we can do. That is the icosahedron. So, boom, 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 boom. And this is what we get. And then what is the math here? N is 3, so I get 1/3 plus 1/5 equals 1/2 plus 1 over epsilon. And again, I've already done this arithmetic over here, down here, and we're going to get that there are in fact 30 edges in a icosahedron. What if you try to do it with what have I done? That's not right. Yikes! That's not an icosahedron. That's garbage. Let's try that again. If you're going to pentagon 3 meeting at a vertex, then that is, of course, the dodecahedron. Woo! There it is. Okay, and so, but anyway, yeah, 30 edges. Okay, and if you try to put pentagons with 4 meeting at a vertex, that's just not going to work. And so what do you get? You get 1/4 plus 1/5 equals 1/2 plus 1 over epsilon. And again, that's just not going to happen because the left-hand side is already less than a half. And so there's no solution. And as n gets bigger, the left-hand side just gets smaller and smaller. And so all of these are impossible. Okay, the last thing, what if you try to do this with hexagons? 3 meeting at a vertex. Can you do that? Well, kind of. And what you get is the hexagonal tiling. And this is 1/3 plus 1/6 equals 1/2 plus 1 over epsilon. And now the left-hand side equals exactly a half. And so once again, you get kind of epsilon equals infinity. But if you try to put more than 3 hexagons together, then again, you get a left-hand side of this equation, which is bigger than, which is less than a half, and so it just can't be done. Okay, so this sort of just completes the entire chart. This is exactly what we did in class, but just kind of better, showing that there are only 5 Platonic solids. And this is a picture that I got from the internet, which strongly inspired this approach I just took. This is sort of the same argument. This chart is organized a little bit differently, but also including, for those of you who are in the know, the hyperbolic case in which you can, in fact, fit sometimes more than... for example, here, what is this? You can fit kind of 4 pentagons meeting at a vertex, but in general, no. Okay, this is going to be continued, but I'm going to stop now. Okay, hello, back a couple hours later. Let's finish this. We ended with a proof that there were only 5 Platonic solids, and now it seems from our chart that we made that what matters is only what kind of shape it is and how many of those shapes are meeting at each vertex. And in fact, this is kind of a triumph in a way. We have completely categorized and described the Platonic solids by their local properties. And so, okay, this is maybe a little grandiose title to the slide, determining the global properties of a regular polyhedron from its local properties. I introduce to you now this thing called a Schlafli symbol. And what is a Schlafli symbol? It's a polyhedron notation, which describes a regular polyhedron by the type of polygon and how many of them are meeting at each vertex. And so we see that the Schlafli symbol for the tetrahedron is 3, 3. Why? Because the first three refers to triangles, and the second three to the fact that 3 triangles meet at each vertex. Here, the cube is given Schlafli symbol 4, 3 because it's composed of squares, so a region faced with 4 sides, with 3 squares meeting at each vertex. An octahedron has Schlafli symbol 3, 4. Is composed of triangles with 4 meeting at a vertex. A dodecahedron is composed of pentagons with 3 meeting at a vertex, and an icosahedron with triangles 5 meeting at a vertex. Okay, and what I would like to do right now is, in some ways this is kind of repetitive, but it's a reverse of the process that we just did previously, sort of in general. And so let's just take, for example, an octahedron. And now, being convinced, okay, let's see, how should we put this? Suppose I just tell you out of nowhere, hey, an octahedron is a polyhedron rather, which is regular, and which has Schlafli symbol. What's the best way of putting this? Okay, I'm using sort of b equals 3 and n equals 4, but that's the notation from our book. But basically, if I tell you that its Schlafli symbol is 3, 4, can we compute from this fact alone all of the other sort of global facts? And by global facts, I mean the total number of vertices, total number of edges, and total number of faces. In some ways, this is just another look at the kind of algebraic relationship from the previous slides, but it's nice to sort of like do it all over again, maybe for like a special case. So, okay, so octahedron, what have I told you? It's composed of triangles, that's what the 3 means, and 4 is the sort of degree of a vertex. Okay, and now I'll go back to maybe like standard notation. What is the standard notation? That we have a certain number of vertices, a certain number of faces, and a certain number of edges, and we've already shown that this is the relationship between them. So what I want to now do is determine what V, F, and E are. At the moment, let's just suppose that at the moment I don't know any of these facts. In other words, this is an exercise which says, hey, I don't know how many vertices an octahedron has, I don't know how many edges an octahedron has, and I don't know how many faces an octahedron has. What I do know is that it's composed of triangles with 4 meeting at a vertex. What can I do? What can I do? It seems that we can just go through sort of the logic from before. So we can say, okay, if there are 4, yeah. So let's count. How do I do this again? Let's count the. So I don't know how many vertices there are, but if I take the number of vertices, which is V, and I multiply by the degree of each vertex, and the degree of each vertex is 4. Sort of that's the local property which is defining the shape. Then if I multiply the number of vertices by the number of edges incident with that vertex, then once again I've double counted all the edges. And now I'll just go back to using just E for edges, I suppose. Okay. Great. So this is the handshake argument again. I think that's explained pretty well. Okay, so well, leaving that alone for a minute, what else? What am I doing? 4V equals... okay, well, I'll just leave that there. And then what's the other one? The other one is that the octahedron is composed of triangles. And so if I take, I don't know how many faces there are, but if I take the number of faces and I multiply by the number of edges bordering each face, which is 3, because the faces are triangular, then once again I've double counted all the edges. And so, is this what I want to do? I guess this is what I want to do. I didn't actually rehearse the exact logic here, but it seems then that I'm looking at my notes, but they're just they're sort of like nothing to me. 3FB equals what? Anyway, all right, and at this point, I now need to do some kind of. Let me just now look at my notes because they're garbage. Let's just do some math now, and what we see is that what's going on? Why is that now so obvious? Why do I know that there are Sorry, one second. I guess I'm just going to put it all in terms of E. This is not what I was sort of expecting to do. Oh man, this flow is all destroyed. Yeah, I guess I could use the equation from the previous slide, but I don't want to. I want to sort of do it all over again from scratch. So, okay, yeah, sure. I guess I'll just put it all in terms of edges. This is not what I wanted to do, but it's fine. So what do I get? I get that the number of edges is half the number of vertices. So 1/2 V. So this is just like a fact. So okay, and I guess yeah, I'll leave it like that, right? Because there are 4 edges meeting at every vertex, and by counting all the vertices, I double count the edges. Then it must mean that this octahedron has the property that there are twice as many edges as vertices. Okay, great. And over here, what am I going to do? Have I just done this wrong also? Wait. Oh my gosh. Video falling apart, but we're going to bring it back in a second by correcting any errors. I'm not even sure that was wrong. I guess I want to solve for V, right? If I want to solve for V, I'm dividing by 4, so 1/2 E. I don't even know what I had written before, but I think that's right now. And over here, okay, getting confidence back, let's just solve for F. What do we get? We get 2/3 E. In other words, I don't know what I said a second ago. That might have been wrong. Yeah, twice as many. The number of edges is twice the number of vertices, and in here, the number of edges is 1.5 times the number of faces. Okay, anyway, point is we plug those back in, and so we get 1/2 E plus 2/3 E minus E equals 2. And okay, what is all that? I guess if we put it all into sixths, then we get 3/6 and 4/6, 7/6 minus 6/6, so 1/6. So 1/6 E equals 2. So E equals 12. And if E equals 12, then what do I conclude from this? Let me just switch colors for no particular reason. If E equals 12, then going back, V has to be 6. And if E is 12, then F has to be 8. So here I have, this is actually very sort of repetitive of what we did in previous slides, to be totally honest, but you're not going to memorize all those formulas, and therefore, here, to me, is a more honest way of doing it, right? In which I only know Euler's polyhedron formula, and I am given the local properties of a octahedron, and from that local property, as promised, I have derived the sort of global properties, which are these 3. Let's do one more, twice as fast and with more confidence. I see now that last year I took a different tack, but I think this is actually better. So okay, let's do it again with a dodecahedron, say. Okay, dodecahedron. Let me again, this time more clearly explain what am I doing. What am I doing? I am taking as the definition of a dodecahedron that the local, well, basically that the Schlafli symbol is 5-3. And I'm pretending that I don't, for the moment, know any of this other information. In other words, I don't know how many faces it has, I don't know how many vertices it has, and I don't know how many edges it has. All I know is that at every vertex, there are 3 pentagons. From that, can I prove all this other stuff? Yes, I can. Once again, I will use V plus F minus E equals 2. This is like the polyhedron formula. And then I again do this handshake argument twice. What do I say? I say, okay, well now, what do I got? At every vertex, every vertex has degree 3 in a dodecahedron because there are 3 pentagons meeting in every vertex. And so if I take the number of vertices, unknown at the moment, times the number of edges meeting at that vertex, then I'm going to get twice the total number of edges, because I double count every edge by counting the number of edges incident with any given vertex. And I perform a similar argument with the faces. I don't know how many faces there are, but if I take the number of faces and I multiply by the number of edges that border each of those faces, well, there are, because the faces are all pentagons, there are 5 edges surrounding every one of these pentagonal faces. And so if I multiply the number of faces times 5, then I've counted every edge, in fact, twice, because every edge borders 2. Every edge is a member of 2 different pentagonal faces. Okay, so this is also twice the number of edges. And thus, for the dodecahedron, I get the following relationship, that the number of vertices is 2/3 the number of edges. And here I get that the number of faces is 2/5 times the number of edges. And now, putting those, I'll put boxes around this for sort of symmetry. So it's the exact same thing, but, you know, practice makes comfort or something. I stick these facts into Euler's form, and then I get 2/3 times the number of edges plus 2/5 times the number of edges minus the number of edges equals 2. So now I have just a linear equation in just one variable. All right, what is 2/3 plus 2/5? Man, I don't know. 10, 10/15ths and... What am I doing? 10/15ths and 6/15ths, so that's 16/15ths. Minus 15/15ths is 1/15th. And then I multiply by 15. So E equals 30. And that proves that there are 30 edges in a dodecahedron. And if there are 30 edges, then to compute the other facts, I just go back to these relationships, and I see that there must be 20 vertices, and there must be, plugging 30 in here, 12 faces. Okay, so I think that's like pretty awesome. I have now, using these, I'm sort of exploring on some kind of level, but one polyhedron at a time now, the relationship between the number of vertices and edges, and also the number of faces and edges. And now, since I have a relationship between the number of vertices, faces, and edges, then I can compute the number of everything. So, okay, I thought that was pretty good. Could have been done a little bit more efficiently, but whatever. Final thing. This is kind of unrelated. Back to graph theory now. Back to graph theory. This is a homework problem from the textbook, but it kind of flows so naturally from what we did in class that it's not better to just do it live. I always go over it live anyway, so I was gonna have to make a video of myself going over it. So instead of assigning it as a homework problem, let's just do it right now. Here it is, and here we see that going back 2 classes or something, we had this deep investigation of these planar graphs. And what we found is that it's very, very hard to prove that a certain graph is not planar. And to show that a graph is planar, you simply produce a planar embedding. And we spent, I don't know, half an hour or something proving that K3 was not planar. And we didn't even prove that K5 was not planar. We sort of left that later as an exercise. So, man, wouldn't it be nice to kind of have some more sort of algebraic properties of a graph that I could use to get a better hold on when a graph is not planar. And this is what this theorem is right now. So this theorem is saying, look, if your graph is planar, simple, and connected, then here is just an absolute fact about the relationship between the number of edges and the number of vertices. If you give me a certain number of vertices, and the way to think about this is, if you give me like 10 vertices, then and you give me only like say 10 edges or something like that, then okay, it's certainly possible for a graph with 10 vertices, but only 10 edges to be planar. In fact, the cycle would be an example. But if you give me 10 vertices, and now you tell me that there are like 75 edges or something like that, okay, keep in mind that the maximum number of edges in a graph with 10 vertices would be 10 choose 2, which is 45. So I take it back. The 75 was a bad answer. 40. Okay, so take 40 edges. If a graph with 10 vertices has 40 edges, well, that's just freaking too many, man. That's nearly all the edges that are possible, which would be 45. And so sort of I feel that the more edges there are, the less of a chance that my graph is planar. And so what this is an absolute limit. This is a formula which will tell you that your graph is certainly not planar if it has sort of too many edges relative to the number of vertices. Okay, you should sort of feel that. And here, by executing the graph of Euler's, by executing the proof of Euler's polyhedron formula on graphs instead of just polyhedra, we've now expanded the category of sort of discrete structures for which Euler's polyhedron formula is applicable. It's not just applicable to polyhedra anymore, it's applicable also to simple planar connected graphs. And so I'm going to use, in a crucial sense, that polyhedron formula right now. Okay, let's just do it, man. And so here, Gossett defines, interestingly, in an exercise, as opposed to in the main body of the text, this thing that we've already been talking about several times, but now we're going to define it precisely: the degree of a region. What is the degree of a region? Well, if you have a planar graph, and by the way, this only makes sense. This concept of a region only makes sense if your graph is planar. If you give me a well, how should I even put this? If you give me some simple planar connected graph. Well, here is a simple planar connected graph, and note that this particular planar embedding divides this the plane up into regions 1, 2, and 3. And the fact that the graph is planar, or more specifically, the fact that this is a planar embedding that I'm looking at, means that the edges don't cross each other, and therefore, like, I have regions. Okay, the entire concept of regions is incoherent if your graph is not planar, or if you have a non-planar embedding. So just to give another example, I can draw K4. What is K4? K4 is the complete, graph with 4 vertices. Here I'm going to draw it in a way that shows that it's just the tetrahedral graph. And yeah, once again, we have 4 regions. But just to sort of be aware that even this same graph, if I draw it in a way, if I produce an embedding which is not a planar embedding, and the way to do this is if you try to draw K4 like this, you find yourself suddenly having a problem because it's not a planar embedding. So hopefully you agree that here the very concept of region doesn't even make any sense. Like this particular planar embedding does not. This particular drawing does not admit of a dissection into regions. Okay, this is just a long-winded way of saying that the very concept of region presupposes that we're talking about a planar embedding. So if you have a region, a particular region in a planar graph, then we can talk about the degree of that region. And the degree of that region is just the number of bounding edges. Okay, good. So I think it's pretty clear then what the let's just execute or not execute. Let's what's the word? Demonstrate or something. This definition with these 2 cases that we've just drawn. So what are the degrees of these regions? Well, the degree of this region is 3 because this is a region with 3 bounding edges. The degree of this region is 4, and then of course the outside region has 1, 2, 3, 4, 5 edges bounding it. Okay, and here also, right, this is 3, 3, 3, and the outside region is 3 as well. Okay, so note that there are some sort of special cases to discuss. For example, what should we do? Because if we're going to define this on any, it's sort of obvious maybe what to do in these situations. But what about more obscure situations like something like this. Well, okay, now let me draw a thing like this, and now let me do like this. Okay, well, this graph is certainly planar, but I'm no longer quite as confident about how to think of this in terms of regions. It's pretty clear that this region on the inside here has degree 4, but what is the degree of the outside? Well, okay, what do we do? Well, Gossett says, hey, it might not be obvious that this is what you're supposed to do, but an edge, this is what he's saying right here, an edge terminating in a degree 1 vertex will be counted twice, once per side. Okay, so that's kind of strange. That is to say, what is a region sort of? What is the okay? What am I supposed to? The number of bounding edges. So think of the boundary of a region as a sort of a door from that region to another region, and on that interpretation, then this region here has degree 4 because there are like 4 ways out of this region. Okay, but this outside region here, what is its degree? Well, its degree is it's certainly there. It's at least 4 because there are 4 ways out of this region, sort of into the other region. But then there's also this door, and this door, this edge, takes you sort of from the region back to itself. And so I want to count this door twice. Okay, and so I don't know if you're going to love this definition immediately, but you will after I explain it a little bit better. The fact is that the degree of this region is 6. Okay, so that explains how to kind of treat these sort of strange cases. So the degree of this region is 6 because basically it is bounded by 6 edges. And you can think of the 6 edges as, this one, this one, this one, this one, and this is a bounding edge for the region because it's a way into or out of the region, and because you can go sort of from either direction, that's that. Okay, but why is this really the definition? The reason that this is really the definition is because we want to apply sort of basic handshake type counting arguments to regions in the same way that we did with vertices. If you recall from like the first day of this unit, and on the first day of this unit, I tried to argue to you that it made sense to refer to the degree of this vertex as 3 and the degree of this vertex as 1. Why? Because we want the degree of this, even though maybe at first this struck you as strange because, in fact, there are only 2 edges incident with this vertex. But we need to count a loop twice because we want it to be the case that the sums of the degrees of all the vertices is equal to twice the number of edges. And here there are just 2 edges. And so it's sort of like everything works out better combinatorially if you agree to count a loop which connects a vertex to itself as contributing sort of twice to the degree of that vertex. And maybe that's already kind of second nature to you or something like that. You can think about this is borrowed from the idea of polyhedra. You can think about this as kind of make a tiny little circle of, radius, I want to say epsilon, but we're already using epsilon. But some infinitesimally small sort of circle. How many edges do you bump into? That, in some sense, is the number of edges that are incident with that vertex. This is kind of like maybe a more intuitive proof for this definition of degree that I stipulated back in the first day of this unit. Well, this is a long explanation, but I think it's a good one. The same thing is happening now. And by the same thing, I mean I want to apply handshake-like principles now to these discussions. Like if you go up here to the sort of this normal one, what's true? Well, I want it to be true that the sum of the degrees of all the regions is twice the number of edges. And of course, that's just true because every region in this normal graph here has a certain number of edges, the degree of that region, and if I sum up all the degrees of those regions, I'm counting all the edges twice, and so that's going to be twice the number of edges. And so it's sort of the motivation for why we insist that this edge here contributes twice to the degree of this region, because
only in that case we agree, of course, here that we have 5 edges, and so we need it to be the case that the degree of this outside region is 6 for this same kind of thing. And so yeah, I mean, you can almost just and then a more intuitive way to think about it is just like walk around the region. How many walls are there, or something like that, right? So start here and then just go 1, 2, 3, 4, 5, 6, and then you're back to where you started. So in some senses, maybe it is the intuitive definition, but you have to accept it. All right, taking forever, so long video. Woo woo. I'm just gonna ignore this because I don't care. But yeah, so that means that you have now maybe some sort of strange situation. Like take this graph. This is certainly a simple planar connected graph. There's only one region, the outside region. What is its degree? And the answer is 4. The degree of this region is 4. Okay, having defined the degree of a region, something I have mentioned previously many times, but now I've given a proper definition and explained all the sort of nuances of it. What's left to do? Do I need notes for this, or is it just all kind of obvious? So let's call this check. What is a lower bound on the degree of the regions in a connected planar simple graph with n greater than or equal to 3? Be sure to include the outer region. What is the lower bound on the degree of the regions? What? Oh, sure. Okay, so this is actually a little bit interesting. Wait, what? Where's the lower bound on the degree of the region? Connected planar simple graph with n greater than or equal to 3. Oh, okay. Crucially, notice that they say n greater than or equal to 3. So you have 3 vertices at least. So if you have 3 vertices at least, then what can we say? Well, if we have 3 vertices at least, let's consider the special case where there are exactly 3. So if there are exactly 3 vertices, then and the graph is connected, then none of these vertices can have degree 0. And so basically, what are the sort of possibilities? How many different sort of non-isomorphic connected graphs with 3 vertices are there? I guess there are just 2, right? There's the one where they're all connected in a triangle. And there's this one, and there's just nothing else, right? That's all there is. There are no other graphs that are simple, connected, and have exactly 3 vertices. Okay, so what is the degree of this region? Well, it's 3, and what's the degree of this outside region? 3. What's the degree of the region here? 4. Okay, and so I guess this is the point. The point is that you just can't have a where's the lower bound? The degree of the regions. So yeah, you just can't have this is the key idea. You just can't have any regions of degree 2. The only way to have a region of degree 2 is if you have a graph with just one edge and 2 vertices. It will be the case that this region has degree 2, but notice that we're insisting that n be greater than or equal to 3 for the moment, just cause. All right, is there any other way to have a region of degree 2? Well, a classic situation of a region with degree 2 would be this one. In fact, it is true here that this region has degree 2 and this outer region has degree 2 also. Notice that this graph satisfies a handshake. But this is not simple because we have 2 edges connecting this vertex. So if we outlaw, if we focus on only simple graphs, that's what we're doing, then we can't have this situation where where you have a region bounded by only 2 edges, and therefore the conclusion of this B is that it's 3. Okay, so good. So the answer to part B, I'm going to sort of just like write this now, is that the degree of any region is guaranteed to be greater than or equal to 3. That's what they wanted you to conclude from part B. What is the lower bound on the degree of the regions in a connected planar simple graph with n greater than or equal to 3? The degree has to be greater than or equal to 3. Just fact. Okay, and yeah, good. So now check. C.
prove that the sum of the degrees of the regions is twice the number of edges. Okay, this is something that we've now been talking about over and over again. I don't need to reprove this. It's just true, right? In fact, it's the entire thing I was explaining for why we defined the degree of a region in the way that we did. Count the degree of every region. Every region has a border with a certain number of edges in it. When you do that, you count every edge twice, and so there we go. Okay, combine parts B and C to show that if there are rho regions, then rho is less than or equal to 2 epsilon over 3. Okay, well, it kind of goes like this. The degree of every region has to be greater than or equal to 3. So therefore, what can I say about the sum of the degrees of all the regions? Where now, if you want to get sort of fancy or something, we're summing from I equals 1 to the number of regions that there are. Okay, so if there are rho regions, and I go through every single region and take the degree of that region and add them all up, then this is the sum from I equals 1 to rho of the degree of region sort of r sub I. Then what do we get? Well, if the degree of every region is greater than or equal to 3, then this has to be greater than or equal to 3 rho, because I'm just adding a number which is greater than or equal to 3, rho times. Okay, but it's also true that by handshake, this is part C, that so C is done. We're sort of on part D now. We've also seen now that the sum of the degrees of all the regions has to be twice the number of edges, and so I get the twice the number of edges is greater than or equal to 3 times the number of regions. And so what we have now is a sort of formal proof that the sum that the number of regions has to be less than or equal to 2/3 times the number of edges. And what went into this proof? Just that it was a simple planar connected graph. Okay, and now, finally, in part E, we say, use Euler's formula to complete the proof of the proposition. What's the proposition? That the number of edges is less than or equal to 3n minus 6. Okay, so I think that now we just do it, right? Just recall Euler's formula. What is it? It's that the number of vertices, well, I guess it doesn't matter how we do this, but yeah, the number of vertices, let's call that n, plus the number of regions minus the number of edges has to be 2. But now we've seen that there is this relationship between rho and 2/3 epsilon. So maybe let's just like solve for rho or something. Yeah, let's do that. So what is rho? Rho is 2 minus n plus epsilon. But also 2, plus epsilon minus n. But also rho is less than or equal to 2/3 epsilon. So therefore 2 minus n plus epsilon is less than or equal to 2/3 epsilon. And now I just do some math or something. So what do we get? 2 plus 1/3 epsilon is less than or equal to n. What am I supposed to be showing again? That epsilon is, multiply through by 3. So 6 plus epsilon is less than or equal to 3n. And there you go. Epsilon is less than or equal to 3n minus 6. All right, fact. This is a hard fact about the relationship between the number of vertices and the number of edges in any simple planar connected graph. What was the logic again? It's actually very reminiscent of what we did on the previous slides, but now abstracting away from merely polyhedra to sort of any planar graph, we can define the degree of a region, even regions which are sort of open in a kind of a sense, and we can use this concept of the degree of a region to perform a handshake-like analysis and find a relationship between the number of regions and the number of edges, or rather the sum of the degrees of the regions and the number of edges. And so, okay, I don't think I need to repeat this all, but basically we see that in any planar simple connected graph, that the degree of the region has to be at least 3. If the degree of the region has to be at least 3, then the sum of the degrees of all the regions has to be at least 3 times the number of regions. But then by a handshake argument, the sum of the degrees of all the regions is just twice the number of edges. Therefore, I get this relationship between the number of regions and the number of edges. And plugging that in to Euler's polyhedra formula and doing some a little bit of algebraic manipulation, I now have a fact. Okay, so this was the proof of this proposition. What can this be used for? Well, the sort of like immediate great thing that we can do with this is we can prove that K5 is not planar. Why? Because now I say that, look, K5 just has too many edges. What is K5? Let's see. I'll squeeze it in. Is there anywhere to squeeze it in? There really kind of isn't. I will squeeze it in here. So what can I say about K5? I say this. That it looks like this. Chomp, chomp. And then jump, 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 and jump, jump. And okay, fact. K5 has only 5 vertices. But n equals 5, but it has 10 edges. So E equals 10. Well, looking down here at this formula says that if your graph is planar, then it must obey this particular inequality, that the number of edges is less than or equal to 3n minus 6. But what does this say? This says that the number of edges has to be less than or equal to 9. But the number of edges is 10. So this graph just can't be planar. So that is kind of incredible. Instead of engaging in this extremely weird proof that we did to show that K33 was not planar, here showing that K5 is not planar was just really easy. Notice that this isn't like a magic bullet. We couldn't use this to prove that K33 is non-planar, because K33 in fact has 6 vertices and only 9 edges. So what does this theorem tell us? This theorem tells us that if there are 6 vertices, then you have to have 12 edges or fewer. But in fact, K33 does have fewer than 12 edges. It has 9 edges, yet still it's not planar. So this isn't a magic bullet, but for certain graphs like K5, it provides a very simple, elegant proof that this graph sort of cannot be planar. Okay, that was very thorough, I think. Let me just redraw this little thing that I drew over here. And I guess I'm just going to end this video. I was shocked to see how long it is. Hopefully you watch it on 2 times speed. Goodbye.